we have this circuit on the left. We want to find the node voltages V1, V2, and V3 that have already been labeled for us. And they're shown as being respect to ground, which is shown there. Okay, we've got a 3-amp source on the left and another source on the right, which is a dependent source equal to 2Ix. And we look at that current, that Ix has been drawn as defined towards the right. Okay, I want to point out that this current, it's already been drawn as pointing towards the right. So we need to be consistent in our calculations to always account for it as flowing towards the right. Okay, so let's talk about the unknowns. Okay, the unknowns in this circuit are, we have V1, V2, and V3. We know those are unknowns. But as we start doing the KCL, or the nodal analysis equations, we're going to find out that Ix shows up in there. So let's start by doing a nodal analysis. Let's do a nodal at node 1. Okay, and again, we're going to use the far minus near approach. All right, so we've got 3 amps, a 3-amp source feeding into node 1, so you get a plus 3 amps. We're going to get a plus, this is going to be far minus near, V2 minus V1 divided by the 2 ohm, plus far minus near, check this out guys, take a look at this far node, V3 minus V1 divided by the 4 ohm. See that? Even though V3 is way over there on the other side of the circuit, it's still connected to V1 through that 4 ohm resistor. So make sure you look around the circuit to identify all the nodes that are connected. So V3 minus V1 over a 4 ohm, all of that is equal to 0. All right, let's do nodal for nodal at node 2. So nodal analysis at node 2, we've got a V1 minus V2 divided by the resistance in between those is 2 ohms. Again, V1 is the far node, V2 is the near node now, right? Plus a 0 minus V2 over 4, plus a V3 minus V2 over 8 ohms. That's the current going through the 8 ohm there, right? Okay, all of that is equal to 0. That is equation 2. All right, well, we're going to need to do one at node 3, right? So let's go and do it. Let's do nodal at node 3. And I'm going to put some underlines under these here so it kind of at least helps keep track of the text a little bit more. So 2Ix, the current source, is actually leaving node 3. Again, that's a current source. Doesn't matter if it's dependent or independent. It's an actual current source. So its direction, we're not assuming that it's into the node. Its direction is shown on the circuit schematic. It's leaving the node. So this is a minus 2Ix plus, okay, node 3 is now the near node. So it's V2 minus V3 over the 8 ohm plus, and again, we still have that same V1 connected all the way over to V3 through that 4 ohm resistor. So we have to account for that term. This is going to be V1 is the far node minus V3 over 4 ohms is all equal to 0. And that is equation 3. Now, we do have 4 unknowns, so we need a 4th equation. In fact, our 4th equation is in finding out that Ix value, and here it is. Ix Well, we can write that in terms of Ohm's law between these node voltages, V1 and V2, divided by that 2 ohm resistor. So Ix, remember, it's been defined as flowing towards the right. So because it's defined as flowing towards the right, we're going to write it that it's V1 minus V2 and not the other way around. We're thinking of it like this. V1 is the plus side, V2 is the negative side, and current is flowing from left to right because it's been drawn that way. So V1 minus V2 over 2 ohms, that is our fourth equation. Now, again, this is by Ohm's law, and the direction is we're not using far minus near. Here, we're actually just doing it. It's based on direction shown for Ix. All right, so that in fact is our fourth equation. Now you could go two ways once you've got this fourth equation. You could take it and plug it into Ix in equation 3, and then you would get, then you'd reduce the system down to 3 equations and 3 unknowns, because equation 3 would no longer have an Ix term in it. Everywhere that you saw Ix, which is just that one place there, would be replaced with a V1 minus V2. And that's a fine way to go. However, what I prefer to do, what I like to do is just put that into another variable in the system. So here's what I'm going to do. We're going to solve this system, a 4x4 system. Where I'm going to let the variables be V1, the unknowns be all the unknowns that we identified, V1, V2, V3, and Ix. Okay, all the voltage, all the variables in your unknowns vector do not have to be the same type. Some of them could be voltages, some of them can be currents. All right, so now we're going to write equation 1, equation 2, equation 3, and equation 4 here. All right, so I'm gonna try to collect the terms. Okay, and so this one again, I'm gonna multiply this. I'm gonna multiply this times -1, and then I'm gonna move the 3 amp source over to the other side. So we're gonna get a 3 amps on this side. Let's collect the terms for V1. So we have a V1 over 2 and a V1 over 4. That again, those will have been, they've been multiplied by -1, so they're going to become positive. So that's 3/4 V1 plus a V2 over 2. So that'd be, again, it's going to flip sign because we multiplied by -1. V3 over 4. It's positive V3 over 4. So again, it's going to flip sign because we multiplied by -1. And then there's no Ix term in this, right? So that's 0 Ix. There's no Ix in that equation. Okay, so V2, let's look at the V1 terms. So V1, we're just going to leave this one positive. Here's a V1. Oops. Let's do this in purple. Here's a V1 over 2. All right, so we're getting a 1/2 V1. We've got, let's do the V2 terms. We've got a -1/2, we've got a -1/4, and we've got a -1/8. Okay, you know, that's going to be 7/8 total. So that's a -7/8. Okay, V3, we've got a positive 1/8 there. And then take a look at equation 2. There's no Ix terms in it, so that's 0. And then the whole thing ends up being equal to 0. So we're good there. Okay, and now let's do equation 3. So we get, for V1, we get a 1/4 V1. For V2, we're getting a 1/8 V2. For V3, we've got a minus 1/8 and a minus 1/4, which ends up being minus 3/8. And then here's a minus 2ix term, right? There actually is an ix term in equation 3, so let's pop that in, and it's minus 2ix is all equal to 0, as we had shown on the other side there. All right, finally, let's do equation number 4. What we need to do is actually write this in terms of all the constants on one side. So this is actually, hang on. This is actually going to be, if I rewrite this, it's minus V1 over 2 minus a plus V2 over 2 plus Ix is all equal to 0. So so we get a 1/2 V1, a 1/2 V2. There's no V3 in that expression. Keep in mind, remember, that makes sense because Ix doesn't depend on V3. It's only dependent on V2. V1 and V2. Yes, thank you. The V1 coefficient should be negative. Thanks. So it's a minus 1/2 on V1, plus a 1/2 V2, plus nothing in V3, plus a 1 Ix is all equal to 0. And now we can go over into MATLAB and pop this into our system. So let's try that. So let's go ahead and type this in. This is going to be 3/4 minus a half minus 3/4, whoops, minus 3/4, 0, okay? And I'm just gonna hit enter to keep my wits about me here. This is 1/2 minus 7/8, 1/8, and 0, and then a semicolon for the next row. This is 1/4, 1/8, minus 3/8. Just trust me that I'm typing this in correctly. This is indeed what we have here on our other slides. I'm just looking at my notes next to me. And then this is minus 1/2 plus a half plus 0 V3 plus 1 Ix. So there's the whole matrix there. All right, there's the matrix A. Let's clear the screen. Type in our vector B. That's just going to be 3, 0, 0, 0 over on the right. So we get 3. One thing you could do if you want to do is just go like this, 3, 0, 0, 0. That's a row vector. And then just hit the apostrophe to transpose it. And now you've got a column vector. So we'll clear the screen, and now we'll just say that X, the solution to all those, which is going to have the values V1, V2, V3, and Ix, is equal to A left divide B. And so we get it's 3.42, 1.7, negative 1.7, and 0.85.